8,200 to 16,400 feet of average erosion of the Colorado Plateau. That's a huge erosion. And I verified, this is another picture of the Colorado Plateau in this area. I verified this in the northern part of the Colorado Plateau by seeing the dip of the strata along the north limb of the San Rafael Swell. The San Rafael Swell is a big bulge up. And the sediments got eroded off of this as it uplifted. So over near Price, Utah, I calculated it because it tilted about 8 degrees to the north. And it was about 25 kilometers long, and there's erosional remnants to the north. So these are dashed lines represent where the strata went over the San Rafael Swell. And I put question marks there because anytime you extrapolate over there, you don't know whether it was the same thickness or thin, but we'll assume the same thickness. So based on just trigonometry, I calculated that there's anywhere, depending on the angle of the strata, and I estimated 6 degrees to 8 degrees tilted to the north. I used a Brunton compass for this, by the way. So the average erosion is 4,200 to 5,100 meters, about 18,000 feet of erosion over the San Rafael Swell there in central Utah. But the erosion has occurred everywhere, just from the literature. And by the way, I completed a study on this to verify this for the Appalachians that will be published in the Creation Research Society Quarterly. 15 to 20,000 feet of erosion over the Appalachians. That's based on the rank of coal and also the amount of sediments off in the continental shelf and slope and rise off the east coast. 20,000 feet in the Flinders Range in south central Australia. 6,500 feet in the southern Canadian Rockies. 10,000 feet the Welsh Mountains of the United Kingdom. 5,000 feet southeast England, 8,000 feet of southern Africa. And these are just a few of them. We've had huge continental erosion, exactly what you expect as the mountains and the continents are rising up out of the floodwaters. I talked about the evidence that we have of the mountains uplifting and the valleys sinking, as well as the ocean basins. And there's huge erosion of the continents. Number 3, this erosional material has to go somewhere. And it goes to the edge of the continental shelf. Now here's a picture from the literature of the continental shelf and slope. It has a really unusual profile. It generally slopes very slightly out to the ocean. Well, first of all, let me give you a little history. The continental shelf and slope is probably one of the most, if you can drain the ocean basins, this would be the most conspicuous landform of the whole earth. This sediment just rings the continents like a bathtub ring. All the continents in the world, and also small islands. It averages about 50 miles, but some of these things are hundreds of miles out there, like the Bering Continental Shelf or the Arctic Ocean Continental Shelf off Siberia. But the shelf is very shallow. It goes way out there. These are sedimentary rocks mostly, and then at the edges is a big drop-off like that called a continental slope. And in many places it changes to the continental rise. And the sediments under this they're thousands of kilometers thick, meters thick. Huge amount of deposition from the continents. This profile is a very unusual profile because if it was natural processes over millions of years, which is the way the evolutionary scientists explain this, you should have a gradual change from the beach right here down to the deep ocean. That's what you should have. And a lot of times you can see the strata in here, and the currents have come from off the ocean because you have little delta features in there that show where the continents came from off the continents, perpendicular and not parallel. Most currents go parallel with the coast today, and that's why you shouldn't have this. Now, Lester King says that the continental margin is mysterious because the shelf it's too wide. It goes out there too far, and towards the outer edge, it just drops off too much. It has a profile of rapid deposition of material coming off as a sheet from the continent and being deposited where the currents slow down in deeper water, which is where they will slow down because they hit deeper water. And so they drop their load. It fits in very well with the flood. And it's against normal wind-generated waves of the ocean surface. See, the average winds determine the average ocean currents. and they're generally parallel with the ocean, and that would distribute the sediments that come in from rivers, you know, in an even fashion, and they would also slump down into the deep ocean. So that's why you should have a more gradual profile. The fourth topic I'm going to talk about, and I'm going to spend more time on this because planation surface, this is an area I spent a lot of time on, are formed. A planation surface, by the definition, first of all, this is erosion surface definition. It's a land surface shaped and subdued by the action of erosion, especially by running water. The term is generally applied to a level or nearly level surface. Okay, if it's nearly level, like it's rolling like that, and it's been eroded, it's called an erosion surface. If it's flat, it's called a planation surface. It's flat as a pancake or planed. And notice they say running water. Why running water? Because you a lot of times find rounded rocks on top of these. And you round rocks by water. Now here's a planation surface in the Bighorn Basin near Graybull. You have dipping valley-fill sedimentary rocks of hard sandstones and soft shales, and they've been sheared off. The same. It's dipping about 30 degrees, and there's your planation surface, and has rounded rocks on it. And this was probably much more extensive, but it got eroded around it. We have planation surfaces all over the earth. And in my area, we have them at 4 different levels in the high plains of Montana and adjacent Canada. This is in the Cypress Hills in southeast Alberta, Canada. This is look at that. That's a planation surface. It's called the Cypress Hills. It's the highest one is 4,800 feet above sea level, about the altitude of here, by the way, while the rivers around it are about 2,500. So it's a real high plateau, but it's as flat as a pancake. Here it is at Reeser Lake. Here it is in Central Park. By the way, it's been dissected by glacial rivers. I find big erratic boulders from the Ice Age that made this valley in here. And then and when you drive up to the top of it, it's as flat as a pancake, like driving across Kansas on the freeway, it reminded me of. And the interesting thing is capped by 75 feet of rounded rocks that don't outcrop in the plains, but come from about 400 miles to the west across the Continental Divide, which I will get into next. We have these all over in Montana, like the top of the Beartooth Mountains is granite, and it's been plain flat. Granite isn't being plain flat today. It's granite, flat surfaces are being destroyed today. So present processes are destroying it. So how can present processes form these things, especially some of these planation surfaces cover thousands of square miles. The Cypress Hills one is 1,000 square miles, by the way. There's some in Africa that cover much of parts of Africa, maybe millions of square miles, planation surfaces. In Wyoming, this is the Wind River Mountains. You have a number of granite mountains that are plain flat, and also some sedimentary ones in Wyoming that are plain right in the Bighorn. This is a planation surface. Actually, this is an erosion surface. See, it's still rolling. And this is in New South Wales. These are vertical sedimentary rocks, and they've been plain flat. This is called the tableland, and it covers all of eastern Australia at the high elevations between 2,000 and 4,000 feet. And this right here was probably a big bulge up of the sedimentary rocks like that, went up like that, something like that, and it got sheared off like that, forming a planation surface, or in this case, erosion surface because it's rolling. But these are worldwide, as Lester King says, a planation of extraordinary smoothness developed over enormous areas in all the continents. Even in Antarctica, you find these planation surfaces on the tops of some of the mountains sticking up out of the ice sheet. From it, most of the world's present scenery has subsequently been carved by renewed erosions. What he's saying is these erosion surfaces once were much larger, but once they were formed, they were whittled down by renewed erosions. In fact, the erosion has probably been so great, you don't see any traces of planation surface in a lot of mountains today. But you do, though, still see maybe a small remnant. And some of them you find big remnants, and plateaus you find still the large areas of them. So planation surfaces are worldwide, global, and common. The fifth and last thing I'm going to talk about is what you find on many of these planation surfaces are rounded, resistant rocks, but I find them in other locations, and I've been documenting these resistant rocks transported long distances, not only around the Rocky Mountains, but also the Appalachians, and I'm reading the literature around the Himalayas and the Tian Shan Mountains in South Central Asia. And I hear from my geology friend in Russia, Dr. Alexander Lalamov, that you have the same signature in Siberia, where it had these resistant rocks go hundreds of miles out into Siberia. So I'm going to talk about one type of resistant rock. It's called quartzite. Quartzite was a sand that got cemented to sandstone and then was heated up and turned to quartzite. Quartzite is a lightly metamorphic sandstone, and when it metamorphosed, sand is mostly glass, or like the windows here, silicon dioxide. It kind of recrystallizes and fills up the pores and becomes non-porous and dense and hard. It's the hardest rock in the Rocky Mountains is quartzite, even around this area. A rock that size, it can hardly break it open with a rock hammer, it's so hard.